Hello fellow problem solvers. So today we're going to be doing a problem from the 2013 IMO Shortlist, problem number N3. I suggest you try this problem out for a minimum of 30 minutes, ideally an hour and a half to 2 hours, but not more than 3.5 hours. If on the other hand you'd like to go along with us, I suggest you put your first ideas out on paper for the next 15 minutes. So now, without further ado, let's begin. So the problem asks us to prove that there are infinitely many n's such that the largest prime divisor of this number, n to the fourth plus n squared plus 1, is equal to the largest prime divisor of this number, n plus 1 to the fourth plus n plus 1 squared plus 1. And now, what's the first thing that you may see? Well, you can play around with small cases and see like what are these prime divisors. But the first thing I saw when I looked at this problem is that, maybe I saw this beforehand, and this is just shows it's useful to solve many problems because you may find similar patterns. This is really n to the fourth plus 2n squared plus 1 minus n squared. And now I can do n squared plus 1 minus n squared, and now this is the difference of squares. And I have n squared minus n plus 1 and n squared plus n plus 1. And now, like, your nth member, like, call this a sequence, f of n is this. You have what the sequence looks like. Really, like, this is for n, this is what it looks like. And when you plug in from n, you go to n plus 1, what you'll get, this will be n plus 1 squared minus n plus 1 plus 1. And this thing right here will be n plus 1 squared plus n plus 1 plus 1. And this thing turns into something. But this thing, what does it become? So we have n squared, 2n minus n, we get a plus n left, plus 1 minus 1, and we're left with 1. So we have this, the same thing we had here, and this other extra thing. So now let's just call g of n is equal to n squared plus n plus 1. And the reason like we're doing this now is because, look, like the greatest prime divisor of f of n will be either in here or in here. The greatest of f of n plus 1 will either be in here or in here. These two things are identical. We need to prove that infinitely many times it's going to be in here and here at the same time. That's really what it is. So now this is g of n. We have f of n is equal to g of n times g of n minus 1. And we must prove that the largest prime divisor of among, that there's infinitely many n's such that among g of n minus 1, g of n, and g of n plus 1, such that among these, the greatest prime divisor of any of these numbers divides g of n. That's what we need to prove. And now with that, with this sort of big introduction, I invite you to pause for another 10 to 20 minutes and try to push the problem further. Here's the next step. So now we say let p of n be the largest prime divisor of g of n. And now if for, like, the contrary would be that for all n greater than some constant starting from some point, these prime divisors always keep increasing or they always keep decreasing. Now, they can't always be decreasing. Also, let's look at, can they be the same? Let's see if that's the case. What if p divides n squared plus n plus 1 and p divides n squared minus n plus 1? Then what do we have? Then we have p divides, when we sum them up, actually no, let's subtract them, then p divides 2n. So p either divides 2, p does not divide 2 because this is here even and then this is odd. So this implies p divides n, i.e. p divides 1, i.e. they do not share any prime factors. So it's never equal, so it's either going to be always increasing or always decreasing. Now, obviously, if it's always decreasing, like you start from any prime and you go to infinity, you're going to run out of primes, right? Because there's a fixed number of primes. So if it's always decreasing, that case is over immediately. So what we need to look at is this case, if it's always increasing. So what happens? That means that p of n minus 1 is less than p of n, less than p of n plus 1, less than p of n plus 2, and so on and so forth. And now the question is, so remember, like, what is p of n? P of n is the largest prime divisor of g of n, which is equal to n squared plus n plus 1. And now this means that this thing the prime divisor of this thing right here will always, always, always be increasing, the largest one. And can you find, is there any contradiction that we can find with this? Is there any special value that this takes? I invite you to take, another 15 minutes and try to figure that out. And here's what it does. It actually does take something, and that's g of n squared is n to the power of 4 plus n squared plus 1. Well, what is this equal to? Well, by our former factorization, this thing right here is g of n times g of n minus 1. And now it means that p of n squared will be equal to the larger of p of n minus 1 and p of n. And now this really solves our problem. That means we can't really have this at all times, because then this would mean we would have this. P of n squared would be greater than both of these, but it's equal to either this one or this one, ergo a contradiction. I believe you can write this up, and this is a cool little problem because it's an n-free at the IMO, and it really has two free major ideas. One is like this whole factorization, and then realizing, wait, these things are actually sort of recursively, like you have parts of like this g of n, like that you have this thing for n plus 1 actually gives you the same thing you had for n. And then you figure out that, okay, like the contrary would be at some point, these always keep increasing or decreasing. You see this is the decreasing one is impossible, and then the increasing one. And the final idea really to solve the problem is this one. Now mind you, we solved this quickly, but this is not an easy problem. It's an n-free from the IMO, that's no joke. But it shows you that even an n-free doesn't have many, wow, insanely difficult ideas. No, it's a couple of nice, cool ideas combined together, and you get a medium difficulty problem. And as always, thanks for problem solving.